This meeting is being recorded.
Okay. So, yeah, I think we can start. Good afternoon, everyone. Thank you for joining this only online Warsaw University Astronomical Observatory Tuesday seminar. And today we have an honor to host Professor Agnieszka Janiuk from Center for Theoretical Physics, Polish Academy of Sciences. Agnieszka did her studies in astronomy at the physics department at the Warsaw University, and then she worked in various places. She did her PhD at Nicolaus Copernicus Astronomical Center, and then she had opportunity to be a fellow in Italy, in the US, in Germany, and also in Las Vegas. She worked as a postdoctoral fellow. Since 2010, she works at the Center for Theoretical Physics of Polish Academy of Sciences, where she even served as a science director. So, and now she's leading the astrophysics group there. She's also a recipient of multiple grants, and actually she received her professorship. We had an honor to be together at the party at the president. So, Agnieszka, the floor is yours, please.
Thank you. Thank you very much, Łukasz, for inviting me to give a seminar at the Warsaw University Astronomical Observatory, and I apologize for not being there in person. I'm sorry for that, but I'm quite far away from Warsaw now. Anyway, I hope to give you this presentation effectively on Zoom, and I hope you hear me well. And yeah, you are welcome to interrupt anytime or just let me know if some technical problems appear. Okay, so the title of my seminar is the viscous torque in turbulent magnetized accretion disks in active galactic nuclei, AGN. And in particular, we are interested in studying these effects on the EMRI, extreme mass ratio in spirals gravitational waves. I will explain now the title in more detail in the introduction section. So I think all of you know what are the active galactic nuclei. I don't need to give many details about this. So just for the start, the active galactic nucleus is a nucleus of a galaxy which brightness is many orders of magnitude higher than the light emitted by all the stars in this galaxy. And we know a lot of AGN in the universe close by and far away from us at various redshifts. And specifically, our own galaxy center is an AGN. And another very famous galaxy shown here is the M87 galaxy, which is also an active galactic nucleus, recently imaged by the Event Horizon Telescope. All of this power making the brightness of the AGN nucleus so enormously large comes from the accretion of gas onto a supermassive black hole, which resides in the center. So what is accretion and what is this viscous torque in the title? I want to remind a few textbook information from King textbook and many other available now. So the accretion proceeds through the disk structure, which is formed because the matter has some orbital motion, namely the angular momentum, and the matter orbits around this massive body, which is the supermassive black hole in case of the AGN nucleus. And we can imagine that this matter forms a series of rings around the nucleus. The rings are at different distances. And this disk rotates differentially because the Keplerian velocity depends on the distance in this way. And because of this differential rotation, the inner rings rotate faster than the outer ones, which leads to the occurrence of a shear stress. And it means that this friction appears and causes the rings to split inward and outward, and the angular momentum is transported. The mechanism of transport of this angular momentum is called viscosity. And there is a quantity defined, namely this viscous torque, which is exerted by the outer rings on the inner ones and vice versa. So mutually exerted torques are formed, and it is shown here by this simple equation coming from the textbook. The torque depends on the distance. Here, distance is denoted by the symbol R. Nu is the kinematic viscosity in this formula, where lambda and V are the mean free path of the gas particles, and V is the thermal speed for molecular transport but also can denote the wavelength and the speed of the turbulence if we have a turbulent transport. Here also there is a quantity denoted by big sigma. Sigma is the surface density because we can easily express all this formalism in the vertically averaged situation when we think just the disk is thin geometrically, so we neglect its thickness and we express all the quantities in the vertically averaged way. Now, the turbulence and viscosity is not a constant. There is no reason to believe that this viscosity is constant throughout the disk, and also it does not have to be constant in time. Probably the hydrodynamic mechanisms cannot produce such a sustained constant turbulence in differentially rotating disks. So the theory of the magnetorotational instability was developed in the early 1990s by Balbus and Hawley, who published a very famous paper about this and provided all the formalism to study the magnetorotational instabilities. And these people found that these magnetorotational instabilities are effective in driving the turbulence. It is shown here in this exemplary cartoon how the magnetorotational instability grows due to the differential rotation of the gas. Here, similarly to the previous slide, you can imagine this inner parcels of the fluid rotating faster than the outer ones because of the Keplerian velocity. These parcels can be connected by the magnetic field lines because the field is frozen into the ionized gas. These field lines are represented here in this cartoon as rings, which means that we can imagine the tension caused at the inner parcels by these springs connecting them to the outer parcels. So this is basically the concept of magnetorotational instability and turbulence in the accretion disks. Now, another acronym which I use it in my title is this EMRIs. What are these mysterious beasts? So extreme mass ratio in spirals are recently very popular hypothetical events where we have supermassive black hole. Here, this supermassive black hole is represented as a potential well. And another smaller mass, many orders of magnitude smaller mass compact object can be also a black hole or a neutron star. And these two compact objects may orbit each other and gradually spiral in due to the emission of gravitational waves. Such small mass black holes or stellar mass black holes or neutron stars can be found in the centers of galaxies. And such systems are now invoked because they can emit gravitational waves while they slowly evolve and complete many cycles before eventually plunging into the supermassive black hole center. Their characteristic strains of this gravitational wave lie in the frequency band of the space-based detectors. The space-based detectors are not available yet, but hopefully they will be available in the near future. So now coming to the gravitational waves, I believe you know a lot about gravitational waves because you have a lecture about this given by Professor Dorota Rosińska, so I don't need to remind The gravitational waves are these transverse deformations of the space-time curvature propagating with the speed of light. The source of gravitational waves is the mass moving with acceleration. So we have such acceleration in case when the two black holes or two neutron stars or two compact objects basically orbit each other. And current terrestrial interferometers detect gravitational waves which have the periods about millisecond or equivalent frequencies on the order of the kilohertz. So compact binaries in our galaxy can be observed by current ground-based interferometers such as LIGO. The future mission space interferometers will be more sensitive to the lower frequencies. Here is marked our interesting range of frequencies where the compact objects of stellar mass are captured by supermassive black holes. Just to remind a few information about current terrestrial gravitational wave observatories. Apart from LIGO shown on the previous slide, we have also Virgo, Kagra, Japanese interferometer, LIGO India under construction now, and the important milestones brought by gravitational wave astronomy are, first of all, the Nobel Prize in Physics awarded in 2017 for the first discovery of the gravitational wave due to the merging of two stellar mass black holes. And more recently, the famous discovery of an association of gravitational wave with the electromagnetic counterpart. In case of two merging neutron stars, people observed also bursts of gamma rays. All right, but about the future interferometer, it is the LISA mission. The LISA mission originally planned design is shown here in this cartoon. The space interferometer will consist of 3 identical spacecraft in orbit around the Sun. Each spacecraft would have targeted the other 2 with lasers. The whole system forms an equilateral triangle. And the size of this triangle is 5 million kilometers long. So the LISA mission is now under preparation. There was a debate how to scale down this triangle. And finally, on January 25th this year, the LISA mission was formally adopted by the European Space Agency. And this is our motivation. So this is our motivation for the study, which I will present now in this main part of the seminar. We want to study the merger of 2 compact objects, namely supermassive black holes or black hole of a supermassive size and the stellar mass black hole in the gas-rich environment, so in the environment of the accretion disk. This supermassive binary black hole merger would produce the millihertz gravitational waves detectable by LISA in future, and such binary systems are usually embedded in accretion disk environment. The recent studies shown already analytically or semi-analytically, I list the references here in this slide. We had several talks in conferences about the recent results that the gravitational waves emitted from the extreme mass ratio in spirals, namely these EMRIs, which I mentioned already, will be sensitive to the plasma environment, and the observable measurable effect could be caused in the form of the gravitational wave phase shift. These previous works, however, they assumed artificial prescription for the viscosity, the famous prescription of Shakura and Sunyaev, where the alpha coefficient is assumed to be a constant. There is a alpha in the range of 0.1, which scales the velocity of the turbulence with the speed of sound, and the scale height of the disk scales the typical wavelength of the turbulence. In our study, we wanted to do more precise estimation for this gravitational wave shift due to the torque in the accretion disk, and we include the magnetic field evolution and numerical simulation of the accretion disk to provide the physical mechanism for the angular momentum transport. So we model the magnetorotational instability and quantify the effect based on the disk evolution. How to describe mathematically and numerically, in the end, the motion of magnetized gas in the gravitational wave field, in the gravitational field of a black hole. Of course, all our methodology is based on the laws of physics. So motion is described by the Euler equation. Magnetic field are described by the Maxwell equation, and gravitational field of a black hole needs to employ the general relativity formalism. So we have all these standard equations of continuity and energy momentum conservation written here in a symbolic way. In addition, we need also equation of state of the gas. The simplest analytic form is the adiabatic equation of state, which can be used, of course, to describe the AGN accretion disk gas. And we evolve numerically our equations. From this textbook form of equations, we go to the equations written in a symbolic numerical form. Here, symbolically, we show how the equations are discretized on the grid. Our grid is composed of many cells. We can have 2 or 3-dimensional simulation of an accretion disk, where we use a spherical polar coordinate system, but the general idea is to express the evolution of the conserved variables. So the conserved variables are composed of the components of the stress energy tensor, and they are evolving due to the change in time of the fluxes, and the source terms can be also present sometimes. However, these fluxes depend on the primitive variables. These primitive variables are those who have a simple physical interpretation, and they are used by the equation of state. So primitive variable is a rest mass density, for instance. It is interesting for us as well. Okay, so the all technicalities are described in the literature. I'm using the code named Harm Cool, and also my postdoc Fatima did her simulation using this code. The code is available on the GitHub repository. Anyone who is interested can download this code and play with it. The code is only CPU version, so we don't have acceleration on the graphic cards in this version of my code. It is, however, nicely parallelized with message passing interface. Outputs are written in ASCII or HDF5 format. In case of 3D simulations, it is important to have a smaller size of the output files. Yeah, now going to the main part. So the problem currently studied is assuming the initial condition, the initial configuration of the thin accretion disk around a black hole. The density profile is written here. The density profile for the thin disk produces such a structure, which you can see here on the left top and middle cartoons. So the polytropic equation of state assumed with index 4/3 is used here. This polytropic index also goes into this density profile. And formula for this f and x functions in general relativistic formulation can be found in the literature. For instance, the India 2021 provide all the formula. So we also assume a topoloidal magnetic field. The topoloidal magnetic field is described here. So it means that the only non-vanishing component of the magnetic vector potential is the A phi component. It results in creation of the radial and polar magnetic field components and parametrization used here with this index M produces more vertically or more radially inclined magnetic fields. These details are a little bit important for the quantitative results. Let me also mention another parameter which we use in our simulations. It is the quantity called beta, which means the ratio of the initial maximum gas pressure to the maximum magnetic pressure in the simulation. And we vary the parameters. The list of parameters of the models is given here in this table. We vary beta, we vary the M index. We also take into account several different values of the black hole spin, but I will already tell you now that this black hole spin does not affect significantly the quantitative results. We evolved several two-dimensional models and one three-dimensional model, which is much more time-consuming, of course, so we don't use too many resources for that kind of model. Okay, and this animation basically shows all what I said. I tried to say in words. The animation shows how the accretion disk structure evolves from this initial condition where you had this aligned magnetic field lines. Now you see the evolved state with turbulence developed here in the equatorial part of the thin accretion disk. You also see kind of an atmosphere above and below the disk plane, and you see the polar region, which is empty funnel. The color scale shows logarithm of density, rest mass density in dimensionless units, and this particular model assumed gas to magnetic pressure ratio of 50, magnetic field index 0.1, and the black hole spin 0.94. This is a summary of final time snapshots of different models, and you can see quantitative differences between those models. So, for instance, this upper row slides show the difference between different beta and also different initial black hole spin. Here, different black hole spin and different magnetic field inclination actually is shown here. This M equals 0.5, while all the other models assume at M equal 0.1. So you immediately see that the magnetic field inclination affects the thickness of the disk. Yeah, here it is a bit thicker, and the turbulence is less developed. While in these all three other models, the disk is still thin and the turbulence is well developed. To quantify the magnitude of the alpha viscosity, we compute directly the components due to the Reynolds and Maxwell stress. They are expressed with this formula where UR, UV are components of the velocity, BR, BV are the components of the force magnetic field. And we do the vertical average and the volume average over the distance from horizon to some chosen radius of the disk where the turbulence is mostly efficient. So you see the resulting quantity for one of the models here. The Maxwell stress dominates, of course, and it is much higher. The Reynolds stress is not that high, but eventually the total alpha is the sum of these two. And our alpha is on the order of 0.3, but of course not constant with time. It varies with time and has some smaller and larger amplitude fluctuations. These results show the evolution of the disk and magnetorotational instability of the analysis. So magnetorotational instability is generally suppressed if the wavelength of this instability is larger than the disk thickness. And you can see here in these four plots our four different models, and the disk thickness is marked here on the right of the panel, and the lambda is marked on the left of the panel. So you see here that the EMRI can be suppressed at some distance from the center of the accretion disk. It means that we go into the magnetically arrested state, which pauses the accretion. And the magnetically arrested state is expressed by such a dimensionless quantity where the phi is the magnetic flux on the black hole horizon, and it is divided by the square root of the mass accretion rate. The threshold quantity is in our unit system is 15. Typically, it is discussed that the magnetorotational instability is suppressed in the magnetically arrested state when this phi is larger than 15. So you see here, most of these models have this situation at late times. And now the final result and the motivation of our work was to compare the viscous and gravitational wave torques. So here this viscous torque, of course, needs to be computed using this alpha. Alpha is coming here to the kinematic viscosity, and our kinematic viscosity is used to compute the viscous torque. We are using such formalism proposed by Shapiro 2013. It is a little bit more precise than the Newtonian one. And we compare this viscous torque to the gravitational wave torque. Here you see the result. The gravitational, the viscous torque to the gravitational wave torque ratio for our different models is on the order of 10 to minus 1, 10 to minus 3 at large, at the distance of about 100 to 200 gravitational radii. So yeah, this is the time averaged radial profile of total of all the cases, and the time average is taken from the second half of the evolution. It is used then to compute the gravitational wave dephasing due to the gas environment. And we found from all this formula that the predicted dephasing due to the gas environment will be on the order of 10 radians for about 10 to 5 in spiral orbits. So is it observable? Of course, difficult to say now since we don't have the observatory yet, but hopefully this kind of measurement can be done in future, and we can quantify our gravitational wave dephasing due to the gas environment. So conclusions from this work are listed here. The initial magnetic field configuration plays an important role to trigger and sustain the magnetorotational instability or suppress the EMRI and turns the disk into the magnetically arrested state. We observed the density-weighted volume averaged alpha viscosity varying around 0.1, 0.25. So it is quantity, of course, a little bit different than those used in previous works, analytical works, where the constant alpha was invoked on the order of 0.01, so 10 times larger. We applied these numerical results from the GR-MHD simulations to estimate the viscous torque in the gaseous environment, and the time average viscous torque can be as large as 1% of the gravitational wave torque for mass ratio of 10 to -3 at radii around 100 gravitational radii in the accretion disk. This extra torque from the environment appears as the phase shift in the gravitational wave signal, and our estimate for the mass ratio 10 to -3, I should stress this, is about 10 radians in 10 to 5 orbits. So thank you very much for your attention. And now I want to make, of course, acknowledgement. First of all, to the PL grid infrastructure, because these calculations were done on the supercomputer ARES in Cyfronet in Kraków. And hopefully we will continue the research, not only because the LISA is adopted, but also because we want to do more precise studies of this kind in proper 3D simulations. And we plan to use the LUMI supercomputer to which we have access also thanks to PL Grid, but this is a much larger and much more powerful machine located in Finland. And I would like to advertise 2 new positions at the Center for Theoretical Physics, which are now advertised on the job register. You can find PhD position announcement and also technical scientific position announcement. So everyone who is interested, please contact me directly or just look into the job register. Thank you.
Thank you very much, Agnieszka. Let me do the virtual clapping. Thank you very much. Questions, comments from people here on Zoom. If you want to say something, then please raise your hand first. Agnieszka cannot see it, but I will direct. I will start. I just have a question about the times you've been showing. So there were no units of time on the x-axis, but also the animation. What is the duration of the simulation?
So we use code units, so to say. Yes, the code units. So final time was about 50,000 orbits. Yeah, 50,000. Yeah.
So kind of
gravitational time. So all is in the units of mass. Time is in the units of mass of the black hole.
But then could you explain this to to observers, like for kind of typical mass ratio you've been simulating here? What is this? Is this days, years, or decades?
No, it's maybe days.
Okay.
Yeah. Mm-hmm.
Okay, that this is more what we can associate.
Yeah. Okay.
Understanding too. Good. I was wondering, because you showed some results for mass ratio 10 to -3, but that's not that very extreme, right? You can expect even higher mass ratios in, as you said, if you take our own galaxy, 10 to 10 to the 6 is the black hole, and then if you swallow a neutron star, then you have the mass ratio of 10 to minus 6, more or less. So have you simulated that low mass ratios?
Well, the mass ratio is a parameter here. This is this Q. Yeah, so we don't simulate this mass ratio. We take it as a parameter, and of course it is a very important parameter. So what I show here is that I quantify these results for a chosen mass ratio, and this 10 to minus 3 is something, yeah, plausible, yeah. But yeah, all this depends on the chosen mass ratio, this Q. Yeah.
Yeah, exactly. Okay, any more questions, comments? Piotr.
Yeah, so I would, it's more like a comment than a question, but I mean, even before Agnieszka, you went to these in spirals, I understand that these simulations are now sort of at such a stage that it's easy to compute or arrive at the value of alpha. I mean, for you, it's like a byproduct, right? That you set up the simulations, you start the simulations, and after a while, you see. I mean, the situation starts from some initial state, and then it saturates, and then it produces the viscosity parameter. So I understand after the 30 years of simulations started, I mean, by Balbus and Hawley, or actually not. I mean, they had the idea that the simulation started after that. Now the simulations are in such a, it's kind of standard simulations that you easily produce alpha, and this alpha 0.1, 0.2, 0.3 is kind of a standard that comes out of these simulations, right?
Yes, exactly. This is exactly as you say. Just let me mention that these simulations are a little bit different than those who estimate alpha through the shearing box, because here we have a kind of global simulation of the accretion disk. And we can measure, of course, alpha at the different locations, from horizon to about a few hundred gravitational radii. We can compute average. I am not showing all the plots here where alpha is plotted at different radius or at different times, but yeah, as a function of time and location. And it is not a small box, it is the whole accretion disk. I mean, the inner part of the accretion disk, but quite a large scale, yeah.
Yeah, that's what I gathered, that it's global simulations, and it's not, I mean, by now it's nothing special to be able to run these simulations, which is great.
Yes, it's nothing special.
Very cool. So I understand this is the work which you recently published with your postdoc, right? Could you show the reference again?
Yeah, I will show the first slide with reference. I'm not the first author. I should acknowledge the very heavy work done by Fateme Hossein Nouri. She left my group already last year, and now she has another postdoc in Italy, in the group of Bruno Giacomazzo, and they work actually on gravitational waves there. More than on the accretion disks. Yeah, but this is the reference. The paper is now in astronomy and astrophysics. Maybe this month will be the electronic version available, but the preprint is of course available. Right. So if you want to see all technical details, yeah, either read the paper or just ask me or Fateme by email. Maybe better her, because she is responsible for all the technical details, especially for the initial conditions testing. Yeah.
Okay, great. Since I don't see any more questions, so thank you, Agnieszka, once again. Thank you all for joining, and see you on some other occasion.
Thank you.
Thank you.